just page after page of really the same concept over and over again. 9, 11, and 12, and then we'll pick up with 13 tomorrow. All right. So how far does Erica start off from school? 22 blocks. What's her distance from school after she has been walking for 4 minutes? 14 blocks. After walking for 6 minutes, Erica stops to look at her subway pass. How long does she stop for? 3 minutes. Erica then walks to a subway station before heading to school, on the subway. How many blocks did she walk to the subway? 2 blocks. How long did it take for her to get to school once she got on the subway train? 4 minutes. All right. So very subtle, but you'll notice how I included the units every single time. All right, so you got to be careful about that. You don't want to throw away points. All right, so interpreting graphs. All right, so we're going to learn about properties, characteristics of graphs. There's some aspects that are obvious, and then there's some that maybe not so obvious. So I'm going to take you through the next couple of pages, and then I'll let you loose. All right, so positive, negative regions, pretty straightforward. The positive region is considered above the x-axis, and the negative region is below the x-axis, and that's because the positive is where y values are greater than 0, and the negative is where the y values are less than 0. All right, so when we're talking about whether our graph is positive or negative, we're talking specifically about the y values. All right. So the positive regions of a function are those intervals where the function is above the x-axis. It is where the y values are positive. Negative regions are where the function is below the x-axis. It's where the function or the y values are negative. All right. Now, the example on what intervals is the function positive. So the little remember statement, it's talking about positive and negative intervals always pertain to the x values, which is kind of a weird thing to think about because we just got through talking about the y values. But really it's just stating for what x values, so I'll actually just write that here, for what x values, so I'll say which x values are the y values positive or greater than 0 or above the x-axis, however you want to think of it. All right, so basically what we're asked to do here is state the domain for which the function is positive. All right, so if we use the point on the x-axis as a cutoff, this would be the location where y values are negative. And this would be the interval where the y values are positive. All right, so all you'd have to do is state the domain, again, domain, interval notation, because what are the intervals for which the y values are positive. So what would that domain be? What's my starting x value and what's my ending x value?
0, 1.
-1 is the correct starting value. We wouldn't want to include it though because it's not positive at -1, right? Because it's on the x-axis, right? That would make it 0. So I want everything to the right of -1. Now, you would, a negative or a positive 1.5, you would think that because this last point occurs at this location, which looks like it's about 1.5, but what's at the end of this curve? An arrow indicating what? Infinity. All right, so going from the x value of -1 to infinity is where this graph would be positive. Where would it be negative? Negative infinity to -1, same type of fencing. All right. Remember, the smaller number always comes first. Right? Negative infinity is smaller than -1. All right. So, and again, because of those arrows, we have to have that negative infinity there. Now, a function is increasing or decreasing depending on its slope. All right. So, increasing means positive slope. Decreasing means negative slope. All right, so the visual way of making that determination is just to look at your graph and read it from left to right. If it's going uphill, as you read it from left to right, it's increasing. If it's going downhill, it's decreasing. If it's a flat line, then it's constant. All right, so a function is increasing if as x increases, y increases. A function is decreasing if as x increases, y decreases. All right. A function is constant if as x increases, what?
It stays the same.
Yeah, it remains the same. So RTS remains the same. That's actually a standard abbreviation, but the weird thing is they don't really allow that on the region, so you have to write remains the same or stays the same. But it's kind of strange. A standard mathematical, like ROC is a standard abbreviation for rate of change, but for whatever reason they don't allow it on the regions. They're just saying that. So on what interval is the function increasing? So again, what I'll do is identify my benchmarks. And then highlight the intervals for which the function is increasing, or the interval or intervals for which the function is increasing. You don't want to look at the arrows, all right? The arrows can be misleading because you look at that arrow on the left-hand side, it's pointing up, and you say, well, it's increasing. The path, sure, the path is increasing, but what we're looking at is how we're moving along that path. You're reading the graph from left to right, which means that you're actually walking or riding along this path, all right? So you're over here, and you're working your way from left to right, so that means you're following the path in this direction. So even though this arrow is pointing up, you're still going down if you're going from left to right, all right? So the only part that's increasing would be the interval that I just highlighted, which is going from what to what, in terms of x only? 0 to 2. All right, now those are solid points there. Those points exist, so it's increasing on the interval of 0 to 2. All right. Now, where it's decreasing, a little bit of a different story. Two intervals, both involving an arrow. So I'm going to have a negative infinity, because again, we're thinking in terms of x. Negative infinity to what?
To 0.
To 0. Solid point at 0. And then from what to what?
2 to infinity.
2 to infinity. All right. Now, when I want to put two sets together, two intervals together, how do I unite those sets? A union with, so a U.
Oh.
right? So max and min points. A maximum or minimum point is a turning point on a graph. That's easy enough to identify. Right? It's actually the 2 points that served as the transition between increasing and decreasing. So that's a pretty good way of representing it. We spend a lot of time in calculus working on this sort of stuff, which is kind of weird because it's in this curriculum now, and then you'll touch on it here and there, but then you'll kind of get it big time once you get the calculus. But it'd be kind of nice if you could hit it now, because you're looking at it like mastering this vocabulary at this moment, and then not really doing a whole heck of a lot with it for a few years. But at least having a good sense of the vocabulary can benefit you. So maximum or minimum is a turning point. I don't know that you need the definition that the maximum is going to be on the hill and the minimum is going to be on the valley, but there it is. All right. So these points are also called extrema. For quality E. These points are referred to as relative maxima or minima. All right. So the extrema is a way of saying max and min. All right. So maximum, minimum, those would be the singulars. Maxima, minima would be the plural. All right. So most people most people live their entire lives without ever feeling the need to say maxima or minima. All right. So max and mins are fine. All right. So all we're really asked to do is identify what would be considered the relative extremes and also the absolute extremes. Okay, so the relative extremes are the highest points compared to the points that immediately surround them. The absolute extremes are the ones that are the highest or lowest compared to the entire graph overall. All right. So in this case here, I would say, just looking at this picture, I'd have an absolute max. They're not asking for this, but I'd say an absolute max at infinity, because this graph is going up to infinity. An absolute minimum at negative infinity. Now, it's kind of hard to think of something as being absolute if it's not finite, right? But really what they're saying is that there is no limit to how high or low this graph could go, all right? What they are asking us for are the relative extrema, the relative mins and maxes, right? And so what we're looking for are the highest points compared to the points that immediately surround them, all right? So the little peaks and valleys along the way. So I have one right here. That's a min, a relative min. They also call it a local min. We also have a relative max. All right, so for relative extrema, what we want to do is state the y values. All right, I want to state the y values for where the function has a max or min. All right, sometimes a question will say, identify the relative extrema and the x values for which they occur. You know, find the maximum height of the object and the time that it reaches the maximum height, things like that. But this is just asking for the highest and lowest points. All right, so what is the y value of the relative min? -1. What is the y value of the highest? 3. All right, so this is one of those nice situations where just by knowing the vocabulary, you're able to easily answer the question.
Yeah, put a box around it.
I just did it so that it was clear what the answer is, because my notes were starting to get messy. Yeah, as long as I can tell what your answer is, it's totally fine. All right, almost there, folks. end behavior. So today's just vocabulary day, really. End behavior refers to the appearance of a graph that's followed farther and farther in either direction as x values get very large, very small. All right, so what that's saying really is, where is the graph going as you go as far as you can to the left and as far as you can to the right? All right. So in this particular graph, as I go as far as I can to the left, so I'm following the path to the left, it's going down forever. All right. Now remember, and this is the thing that really ends up being a hang up for a lot of folks, this notation is replaceable with y. All right, so this is the same as y going to negative infinity. All right, same idea with the other notation. So this is the same as y going to positive infinity. All right. So as I go as far as I can to the right, the graph is going up towards positive infinity. All right, that's all end behavior is telling us. Like, how is it behaving at its end? Is it approaching a particular number, a finite value, or is it approaching some kind of infinity? If it's going up forever, it's going to positive infinity. If it's going down forever, it's going to negative infinity. Or it might be targeting some particular value, in which case it's going to like 2. You know, it could be anything. Right? So the way we would state it is just the way it was structured there. As x approaches negative infinity, and as x approaches positive infinity, we'd make a statement of what f of x is approaching. All right, so taking a look at this graph, as x approaches negative infinity, that's just a notation to say, if I were to continue going forever to the left, where would my y values go? So trace it along with your finger. If you're following the path and you're continuing to go to the left, where's the graph going? Infinity. Trace it to the right. I'm going to the right. My movement is definitely in the rightward direction. Where's the graph going? Negative infinity. Those exaggerated hand movements tend to kind of get the job done. All right, so you know that can be probably the most helpful way to do it. All right, if you're given a function, so if you're given an equation, it says, instead of giving you the graph, it says f of x equals 3x cubed minus 2x squared plus blah 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 blah. You might look at that and say, well, I have no idea how to do that. You didn't go over that in class. Well, you have one of these. All right, which means that you could very easily come up with one of those. All right, so if you're given an equation, you're just a few keystrokes away from having a graph to look at in order to make the determination of pretty much all this stuff. All right, so hopefully that makes some sense. Anyway, your practice is really unlimited.